All right, starting over again, we'll continue where we left off on Monday, dealing with exponential functions. So you'll see here that we want to look at different functions and how to differentiate them, but also make sure you see the second one we want to focus on, like what are some things we use differentiation for, okay? Now, when you look at the derivative of this first function, make sure you see here that you're going to have to use the product rule. We have two different functions in their own right that we're multiplying together. So we're going to have to first times the derivative of the second, and then we're going to add that with the derivative of the first times the second, okay? So that'll give us 2x squared e to the x plus 4x e to the x. Now, may not look like we did the derivative, but we definitely need to remember that when you take the derivative of e to the x, it equals e to the x. That's one of the things that we looked at on Monday. Is there any questions or concerns with that first one? All right, so moving on to the second one then here, we have to deal with identifying all x values where there is a horizontal tangent. All right, so what we're looking at here, when we see a horizontal tangent, we're thinking of like slopes that are equal to 0. That's one thing you want to make sure when we say horizontal tangent, we're thinking of a slope that's equal to 0. Now, this isn't just any slope. This is where we look at that instantaneous rate of change. Well, that's what the derivative gives us, right? So what we want to do is take this function and we want to differentiate. So we're going to say g prime of x equals, and we need to differentiate this. Well, the derivative of x, that's just 1. Now be careful with e to the 2x because we have to do the chain rule. So we'll have minus e to the 2x times 2. So what we're seeing there is the derivative of e to the 2x is e to the 2x, but then the derivative of 2x is 2. So we want to be careful with that. Going through this then, just to clean it up a little bit, we'll have 1 minus 2e to the 2x. Now, horizontal tangent lines, remember, that's where we want to look at the slope of a 0. So this function gives us all of our instantaneous slopes, right? It gives us that instantaneous rate of change at any x value. So what you want to do here is say, hey, where does this function equal 0? The derivative equals 0. That's going to help me out here. Well, if you set this equal to 0, we get to this statement here. 1/2 equals e to the 2x. Now, the 1/2 e equal to 2x is something that we haven't necessarily come across a lot so far this semester. But this is where we're talking about dealing with exponential logarithms, okay? So I kind of talked about it a little bit. I didn't go full details, but when you have y equals a to the x, right, its inverse, this is the inverse of this, and we need it to help us solve, is the natural log of y, not natural log, I'm sorry, the log base a of y equal to the log base a of a to the x. The reason we like that, that'll give us log base a of y equal to x. This is an identity property that we need to make sure we recall. And I got a list of them here in a second that you can take a screenshot of or a picture of. But that's where this x comes from. That allows me to solve for something that's in the exponent. Okay. Now what happens here though, since I have base e, that's where the natural log comes in. You can say, hey, this is the natural log of 1/2 equal to 2x. as you see here, this side over here should work out nicely. We want that to happen. So when you do the natural log of both sides, the natural log of e to the x is just x. And then make sure you see here, though, we do have one more step that we need to work through. Because at x equal to 1/2 times the natural log of 1/2, we have a horizontal tangent. Now, as we've talked about as well in class, this is one of those situations where, hey, we have an exact value, but at some point we would probably need to put this in to get an approximation, right? Use decimal values. Okay. So I do encourage you, make sure you're comfortable finding it on your calculator so that you know how to get to the decimal value, right? So when you look this up, make sure that you're getting to negative 0.36, oops, 3466 is approximately what we're looking at. Any questions with the second one I can help with? All right. Well, let's continue with this, right? Let's look at a application problem where it's talking about what they're going to call marginal cost. Okay, so we've looked at different cost, revenue functions, profit functions. Here's one that's dealing with the marginal cost. Okay, make sure you see here they're giving us the total cost. That's where C of T comes in. So we have this function here. They give us the graph. We're not really worried about negative numbers, right? Because T is in time and years since start date. So this is going to be when it started and then moving forward 1 year at a time. So we don't want anything over here because we don't want the before start date. Okay. What they want us to do down here, though, is using this function is first find the marginal cost. Now make sure you see with the marginal cost, that is its own function. That's where the derivative comes in. So as we look at this cost function, the marginal cost is going to come from the derivative. Now, when we look at this, when you have C of T equal to 200 minus 40 times e to the negative T, it kind of follows like that first one we did, right? The difference here is, though, when you do the derivative, right, we get 0 minus 40 times e to the negative T times -1. So this term was constant, so it goes to 0. And when we do this, we get a -1 instead of the 2. Okay, so be careful with your signs here, because what we're going to eventually have is a negative and a negative multiplied together. So the marginal cost function will be 40 e to the negative T. As I mentioned on Monday, and I'll always kind of remind us here, especially as we start dealing with more and more varieties of functions, always watch out for that chain rule. So the derivative of e to the negative T is e to the negative T, but the derivative of negative T, that's where that -1's coming from. Okay. Now, with that said, the next thing they wanted me to do is go find the marginal cost at when the year is 0, when they first started up. So if we take the function we just found and plug in 0, well, that's just going to equal 40 because anything to the 0 equals 1. Doesn't matter the base, right? So e to the 0 is 1, so 40 times 1 is just 40. Now, one thing we have to be careful of is make sure to go back and look at what this is about, right? It says in millions of dollars, right? So it'd be $40 million per year. This is definitely an important part you want to make sure to pay attention to as well, because whenever you start dealing with this is a rate of change now. This isn't just dollars, right? That's where the total cost up here is in dollars. This is a rate of change now. We differentiate it with respect to t, which is our time. So that's where that dollar over time becomes an important aspect. So that's why you definitely want to make sure to say, hey, that's $40 million per year. Now, one thing to make sure to interpret from this, as we've talked about in class, make sure you see this is increasing, right? That's a positive $40 million, right? The next thing they want us to do is look at it at year 5. Let's go check it out at year 5, but make sure you see it says round to the nearest thousand. So this will give us 40 times e to the negative 5. All right, so if you use your calculator, you get to this decimal approximation here. Now, keep in mind, as we already started off with, we're talking about millions of dollars. So whenever you get this decimal approximation, you want to times it by 1 million. That will give us this value. Let me make sure I multiply that correctly real quick. Yeah, okay. Now, the reason I'm showing this is make sure you go back to when it says round to the nearest thousand. They want me to round to this digit here. So I want to say that this is actually approximately $270,000. And then again, per year. So as we look at the 5th year of this business, the marginal cost is going to be $270,000 per year. Which if you compare, like, hey, the first year it was a lot more. Now it's not as much. As we go from year 4 to year 5, it's still increasing, but it's not increasing like it did that first year. That first year increased a lot. Okay. Think about like startup cost, what it's taking to get this thing going. Are there any questions with these two problems here, though, using the marginal cost function and plugging stuff in? All right. So the next thing then, let's pull it on a slide of its own. So we have our cost function and we have our marginal cost function. What they want us to do is look at these as we approach the far right end of our x-axis. So what happens if we just try to go all the way down to positive infinity on the x-axis? All right, so if you look at the original function here, this is one of the reasons why the graph is helpful. All right, what you should see is that there's kind of an imaginary line that this thing cannot cross over. And that's where we kind of talked a little bit about asymptotes. Now, if you remember what we talked about with the graphs on Monday, so see if we can pull one up real quick to show it. We graphed something that was exponential on Monday. We showed that there's going to be a horizontal asymptote. All right, this horizontal asymptote affected the range or the output values of our function. So right now we're looking at the limit to see kind of what's going on. Well, the nice thing is, if you remember, we can use the limit to help explain that, but we can also kind of see it ahead of time. So as we come over here to the function that we're working with now, so if we look at this one first, because that's what they want me to do, is look at these two separately. We have the limit as t goes to infinity of 200 minus 40 e to the negative t. Now, from a limit perspective, a better way to write this is limit as t goes to infinity of 200 minus 40 over e to the t. Now, the reason I'm changing it is one things I kind of briefly talked about is anytime you're dealing with a limit of infinity, this is definitely something you like to see, because as this goes to infinity, right? E of t is going to just keep getting bigger forever. The whole fraction itself is actually going to go to zero. Right? If you think about something like this, like, hey, I have 1 over 2, 1 over 4, 1 over 8. If I had bases of 2 instead of e that are being 2 times 2, 2 squared, and so on, 2 cubed, if you keep going, when the denominator keeps getting bigger, the fraction itself is actually getting smaller and getting closer to zero. So that's what we're using here. This is just a more mathematical way to say, hey, as I look at this limit, as t approaches infinity of that original function, it's going to equal that 200. Now, what you're seeing is the total cost for the company in millions of dollars per year, or in a year, sorry, in a year, will be capped at 200 million. All right, so this is 200. Remember, working in millions. That'll be the cap for the total cost. Now, as far as dealing with that is concerned, the marginal cost shows us how much that total cost will change each year. So when I deal with the limit here, as t goes to infinity of the 40 e to the negative t, as we just explained, this is the same term we had before. So this is going to go to zero as I go out to infinity. What you see here, this flattening, the marginal cost is going to do it in this way. So the flattening occurs here at the x-axis. So I'm never actually going to get to zero, but hey, the limit allows me to just say, hey, it's going to approach zero, which means as time passes on, it's going to get to a point that the total cost should not increase from one year to the next. The change will be so small that you won't even see it taking place. So we'll call it zero. At that point, going from mathematics to practical application, there would be no change in the cost. Okay. Now, the question here that they put is, why do you think the company's cost tends to level off as time passes? Right. So as you look over here, as we talked about, the startup cost to get a business going was pretty high. But even in the year 5, the change in total cost was not near what it was to start it. What this adds is at some point, the total cost will not increase anymore. Okay. Now, one thing I was reading is kind of thinking about this, like say you're owning a bakery in town. All right. With your bakery, right, you start off with, say, 1 oven and 2 bakers. Well, guess what? You have room to add 2 more ovens. So you put 2 more ovens in, right? There's some costs that as time goes on, like, hey, our demand allows us to make more bread and cakes and stuff. Well, if with 2 more ovens, hey, let's get some more bakers. The problem that you run into, though, and this is where Can y'all hear me now? All right, sorry about that. I don't know what happened. So as I was trying to explain here, though, when you look at the total costs, right, it started off really high because you're getting the business started, right? So if you're looking at a bakery, you got to buy ovens, you got to buy mixers. There's a lot of things that you got to do to get started. Over time, as your business grows into that facility you have room for more ovens, but you can't add an unlimited number of ovens, right? There's going to be a limit on how many ovens, mixers you can actually have. The same will be true, say, for bakers. You might start off with one or two bakers and add more bakers as you go. But if you add too many bakers, right, instead of being more productive, people might start getting each other's way, right? So there's kind of a limit on how many bakers you can have in there actually doing the work throughout the day. So those would be some kind of ideas you can look at as why the cost will tend to level off as time passes. Okay. Now I got my mic back on. Sorry about that. Is there any questions about this particular problem I could help someone feel better about? All right. It looked like I was still getting microphone though whenever I started this problem. So if I missed anything, please let me know. Now, the next thing we need to look at then is, hey, as we've introduced logarithms, right? We need them. So first and foremost, make sure you're familiar with your properties of logarithms. Okay. One of the things, if you need to, they do have it. Let me try to find it again. In our book, if you go to the one on Pearson, they have all of it for the natural log, but you'll see here, this is still the same kind of what I had on there with the other properties. But remember, we're going to work probably a little bit more with base E, since that keeps a little bit more consistent with what we need from an application standpoint. Okay. So what you'll see here is this is more generalized, but for the natural log, so like when I say the natural log of X, what we're really saying is log base E of X. So all these things will hold true. Okay. Now, the change of base formula, you do not need when you have a natural log because it's already with something a calculator can use. This is something you kind of need when dealing with calculators. Like if I said log base 2 of 4, well, hey, 2 squared is 4. But once I do log base 2 of 7, well, 7 is not a power of 2. So that's where calculator and the change of base formula will help you. Okay. Now, with that said, our focus is definitely going to be on logarithms that are base E for the most part. When we need other ones, we'll make sure to walk through those. Okay. But what we want to do, since we haven't looked at it yet, is we need to talk about what happens as far as differentiating the logarithmic function. Okay. The good news is with our properties in place, we can actually build something here. Okay. So from this first equation, make sure you see here, as I mentioned, to solve this, oops, to solve this equation, I had to use the natural log of both sides, right? So we took the logarithm of both sides. This one works out nicely because of our properties. As I've restated here, that would kind of filter into this one, which is more appropriately written this way. Okay. What you'll find here is as you could take the logarithm of both sides, you can also exponentiate both sides. So I'm going to use base E since I'm working with the natural log, but I'm going to make both sides an exponent of E. So that's called exponentiating my equation. Whatever I do to one side, though, we do the same thing. The reason we like this, over here, we'll just leave this as E to the F of X. Over here, that gives me just X. All right. This, again, focuses on this property here. Another way to write that property, though, it's not written here like that. But you could also write this property as a to the log base A of k equals k. It's a similar way to write that property. Now, the reason we like this now is both sides are something we know how to differentiate. So now we can go in and take the derivative of both sides. Make sure you see here that as we do the derivative, that the derivative of e to the f of x is f of x, but I have to multiply using the chain rule by the derivative of f of x. Okay. On the other side, the derivative of x is just 1. So here's the derivative of that. The derivative of this is itself. And then the chain rule, I need to take the derivative of the exponent. Now, what that allows me to do now, forget what I'm writing to, is I can divide both sides by e to the f of x, right? Because what that's going to give me is the derivative function that we're looking for. F prime of x equals 1 over e to the f of x. Now, we don't want to keep the f of x in there, though. We already know what f of x is, so we can actually go plug that back in. So it'd be 1 over e to the natural log of x as an exponent. Now, what you find is one step further we can add to this. We've already talked about what e to the natural log of x is, right? Using our inverse properties of exponential and logarithms, that's going to be just 1 over x. What that means to me then is, hey, if f of x is the natural log of x, then the derivative of that is 1 over x. Or another way to write that, just to make sure we have consistency in how we write it, the derivative of the natural log of x equals 1 over x. Now, I felt like this is a great way to show it, though, because, hey, this introduces or reminds us of something we need for solving exponential or logarithmic equations, okay? But then it brings us to derivatives that we should know, okay? Like the derivative of a linear term is just the coefficient. The derivative of e to any exponent is itself, but just make sure, again, as we've talked about a few times now, is the chain rule, right? I got to take the derivative of that exponent that I started with, okay? The helpful thing here is as you see, once I get this by itself, so dividing both sides, I now have the derivative, which is what I was trying to do, is differentiate the function. Just make sure you see here, anytime you take an approach like this, where I have f of x and the f prime of x, we need to plug back in what f of x was. We don't want to keep it as f of x. We want to go back to like, hey, this is what f of x is, plugging in. And here we can simplify. Sometimes you won't be able to, but for this problem, we were able to, which gives us this nice little statement. So any questions with where I'm getting this from as far as a new derivative that we're learning? All right. So the next thing is let's put this to practice. We have a couple more minutes left, so let's look at these two functions and let's take the derivative of both of them. Now, as you can see, both of them have the natural log in them. All right. So what we need to make sure we remember is that new derivative that we just defined, which is, hey, if I differentiate the natural log of x with respect to x, I will get 1 over x. Now, another way to make sure that we remember this, though, that highlights the chain rule. If you differentiate with respect to x and you have the natural log of some function of x, so like u of x, make sure you see here that that's going to give us 1 over whatever was the argument of logarithm times the chain rule, which is the derivative of whatever that argument was. So be careful to pay attention to that chain rule here as well. That doesn't go away. Now, looking at this first function, right, we have a coefficient times natural log of x by itself. So we can just do a direct use of the derivative. So if we differentiate y with respect to x, this will give me -5 times what we just learned, 1 over x. So we could just write that as -5 over x. Any questions with the first one? All right, so the second one we have to be careful because now we're going back to that product rule, right? I have two different things that I'm multiplying together that have the x involved. So this time I have to use the product rule. You could have used the product rule on this first one, but hey, just remember the derivative of -5 would have been 0. So one of the terms would have went to 0. Over here, though, that's definitely not going to be 0 when we take the derivative of it. So we need to make sure that we're careful with our product rule. So we'll do first times the derivative of the second. Okay. Now the derivative of the natural log is 1 over its argument. In this case, it's 3x. But because it is 3x, I have to make sure to look at, hey, what is the derivative of that 3x? Okay, and that's where the chain rule comes in, because I'm going to need to multiply by that. So that's where the chain rule comes in here. With that said, though, when you do, you're going to add the derivative of the second one, you'll have 2x natural log of 3x for that second term. At that point, all we need to do is just clean it up a little bit. So we'll say, hey, the derivative of h of x is equal to x plus 2x natural log of 3x. Make sure you see here, these threes divide together. And then I could take 1 away from this x because of the x that was in the denominator. So that's what's going to allow us to clean this up a little bit. Which just kind of make sure to point out, like we started with, if I ever wanted you to find the horizontal tangents here, having it cleaned up is definitely helpful, because you could say, hey, I have this statement equal to 0 now. We could factor out an x because both terms have x on them. And one of these zeros is going to be x equal to 0. Now, there's different conversations we're going to have about this, because as I mentioned before, critical points, right, are not always horizontal tangents. So one thing you'll find here is, as I deal with the natural log, we have to make sure to remember it's an inverse itself. When we looked at this quick graph situation, right, an exponential had a horizontal asymptote. So that's where this graph comes in, right? As you approach negative infinity here, as x approaches negative infinity here, going all the way out here, we approach 0, but we'll never actually get to 0. Well, when you do the inverse of that, that horizontal tangent now becomes a vertical tangent line. So when you look at the natural log of x, which is what's being graphed here, we can't actually use x equal to 0. That's not allowed. So when we go back to the function we're looking at here, there's going to be certain things that we have to keep in mind, like, hey, x has to be greater than 0. I can't use 0. I can't use negative numbers because of that vertical asymptote. Okay. Now, is everyone okay with where I'm getting this from as far as the derivative is concerned? Right. Keep in mind, like I said, this is just me making sure to say, hey, always keep in mind that we're cleaning up because we're probably going to have other things we need to do with stuff moving forward. And this was that second problem we started off with today, is finding that horizontal tangent line. The other problem you would have to deal with that other factor, but it's going to end up working out to where you're going to have e to some exponent, kind of like what we saw with that first. Okay. Now we have a couple more minutes left, so let's look at an application problem that involves the logarithm here. All right, so here's a company's dealing with some advertising. It says a model for a consumer's response to advertising is given by the N of A. Okay. Where you'll see a restriction to the domain here. What they're saying is, hey, at least one advertisement but more advertisements possible. Okay, N of A, right? The function N here represents the number of units sold. The A value is the amount spent on advertising. So they're spending at least $1,000, right? Because it's in thousands of dollars. Right? So what they want us to do here is just make sure we use the function. So plug in for the natural log. So this first one is saying how much is it after you spend $1,000, but be careful here. A is in thousands of dollars. So what that means is you have to make sure interpret that, hey, what they really want me to do is A is 1. It's definitely something you want to be careful of. So when you go use that original function and you plug 1 into it, you get 2,000 plus 500. Oops. Times the natural log of 1. Now, when you're dealing with this, you're saying e to what exponent equals 1. That's what the natural log of 1 is giving us. We're trying to find that exponent. What you're going to find there, anything to the 0 is equal to 1. So that means the natural log of 1 is 0. Okay. Definitely want to make sure to review some of those things so you're comfortable with them. Well, 0 times 500 is 0. So that means that, hey, when you spend $1,000 on advertisement, we should expect to sell 2,000 units. Now, the next thing they want us to look at is the rate of change for the number of units sold per $1,000 spent on advertising. Okay, how do I know that's what they're talking about? Well, they want me to find the derivative of this now. Okay, we only have a couple minutes left, so I'm going to focus on this one, and we'll pick up on this one, have that discussion later. But make sure you see here as you deal with that, whenever you see the notation here that we have, this is them telling me to find the derivative of our function. That's where the rate of change comes in that says, hey, how much will the number of units change, right, as we change the thousands of dollars that are being used for advertising. As we deal with this, though, make sure, again, you'll see here a constant term goes to 0 plus 500 because that's just coefficient. But the derivative of the natural log of A, well, that's where that 1 over A is going to come from. So when you do this, the derivative function of N is just going to be 500 all over A. So we see a ratio here that's going to give us what we're looking for. Now, what they want me to do now is say, what's going on when we spend $10,000 on advertising, right? We definitely want to pay attention. Is it going up or is it going down? What's going on? Let's look into this. So when I deal with this, N of 10 equals 500 all over 10, which will equal 50. So we expect the number of units sold at $10,000 to be increasing by 50. So there will be 50 more units per the $10,000 spent on advertising. Now, the reason I say 50 more is because, again, make sure you see here that the 50 being positive is how I know it's increasing. Is there any questions or concerns here with this as far as the derivative is concerned, where I'm going from this function to this function? All right. And as I said, we only have about 3 minutes left. So I feel like this is a good place to pick up, though, because as we deal with this, we kind of started talking about this, but I wanted to make sure to introduce all the functions we're going to need before we go into it. So this will be a good conversation for us to pick up on as we move into next week. Okay. Now, one thing I want to make sure to point out is just don't forget we do not have class on Monday or on Monday next week. So I won't see you again until Wednesday. Now, right now, I should be present, be able to attend class in person Wednesday, but keep an eye on announcements because depending on what happens with my children's schooling and my wife's job will determine what happens if I have to be home with them or not. So just keeping an eye on announcements before you head out to class on Wednesday. I'll make sure to do my best to post either way that, hey, I will be in person or I will not be in person. Okay. I do apologize again about having to do this today, but sick children I had to be home with. So please forgive me. And then I hope this helped moving forward. Okay. If you don't have any questions or concerns, though, have a great weekend and enjoy your break. And I will see you on Wednesday.